Section 3.7, Implicit Differentiation. So in class today we learned what implicit differentiation is. Now we're just going to apply that process to various problems and extend our knowledge of implicit differentiation. So on the top of your paper I've notated the steps for the process. So you want to differentiate both sides of the equation with respect to x. You can use power rule, product rule, quotient rule, chain rule, etc. Then you want to get all the dy dx terms to one side of your equation, factor out the dy dx, and then solve for dy dx. So our first example should look similar to ones that we did in class today. So if we want to find dy dx of x to the fifth plus 4xy cubed minus y to the fifth equals 2, we want to find d dx of x to the fifth plus d dx of 4xy cubed minus d dx of y to the fifth equals d dx of 2. Okay, so the derivative of x to the fifth we know is 5x to the fourth, and then to that we're going to add the derivative of 4xy to the third is a product rule problem. So we have a u and we have a v. So just on the side, I'm going to write these out. So u is 4x, u prime will be 4, v is y cubed, v prime will be 3y squared dy dx. And then we have u, v prime plus v, u prime. So we have 4x times 3y squared dy dx plus y cubed times 4. And then we're going to subtract derivative of y to the fifth, which is 5y to the fourth dy dx, and the derivative of 2 is 0. Now to simplify everything, we have 5x to the fourth plus, we can multiply these, so we have 12xy squared dy dx plus 4y cubed minus 5y to the fourth dy dx equals 0. Okay, so we want to collect all of our dy dx terms onto one side. So we'll move this term and this term. So we have 5x to the fourth plus 4y cubed equals negative 12xy squared dy dx plus 5y to the fourth dy dx. Now we want to factor out our dy dx terms. So we have 5x to the fourth plus 4y cubed equals dy dx times negative 12xy squared plus 5y to the fourth. And when we solve for dy dx, we get 5 x to the fourth plus 4y cubed over negative 12x y squared plus 5y to the fourth. So now we're going to use implicit differentiation to determine the equation of a tangent at the point negative 2, 1. So the first thing we want to do is implicitly differentiate x cubed minus 4xy minus 3y cubed. So we have d dx of x cubed minus d dx of 4xy minus d dx of 3y cubed equals d dx of negative 3. So the derivative of x cubed, we know is 3x squared. And then we're going to subtract. Here we have quotient rule. So 4x is my u, y is my v. So u prime is 4, and v prime is dy dx. And we want u, v prime plus v, u prime. So we have 4x dy dx plus 4y. And then we'll subtract the derivative of 3y cubed, which will give me 9y squared dy dx, and the derivative of negative 3 is 0. So simplify, I get 3x squared minus 4x dy dx minus 4y minus 9y squared dy dx equals 0. So we'll move all the dy dx terms so that they're on the same side. So that's the minus 4x dy dx and the minus 9y squared dy dx. So we have 3x squared minus 4y equals 4x dy dx plus 9y squared dy dx. Factor out my dy dx, I get 3x squared minus 4y equals dy dx times 4x plus 9y squared. And solve for dy dx, I get that dy dx is equal to 3x squared minus 4y over 4x plus 9y squared. Okay, so I found dy dx. Now I want to use that at the point negative 2, 1. So I'm going to use this for dy dx at the point negative 2, 1. So for x, I'm going to plug in negative 2. For y, I'm going to plug in 1. So I have 3 times negative 2 squared minus 4 times 1 over 4 times negative 2 plus 9 times 1 squared. Which is 12 minus 4 over negative 8 plus 9, which gives us 8 over negative 1. Sorry, 8 over 1, which is just 8. So this is my slope at the point negative 2, 1. So to write my final equation in y minus y1 equals mx minus x1, I know y is 1, so y minus 1 equals my slope of 8, x minus negative 2, so x plus 2. And that is the equation of the tangent to x cubed minus 4xy minus 3y cubed equals negative 3 at the point negative 2, 1. So let's now flip over to the next side. So for number 3, it wants us to find the second derivative of the equation 2x cubed minus 3y squared plus 10 equals 0 at the point 1, 2. So I'm going to split this paper in half because we're going to find the first derivative, then we'll use that to find our second derivative. So our first derivative, we want d dx of 2x cubed minus d dx of 3y squared plus d dx of 10 equals 0, right? The derivative of 0 is 0. So derivative here, we get 6x squared minus the derivative here, we get 6y dy dx plus the derivative of 10 is 0, and that's going to equal 0. So to move so that my dy dx term is in one place, I'm just going to move that 6x squared over, so we have negative 6y dy dx equal to negative 6x squared. And then to get dy dx alone, divide by negative 6y. So dy dx is equal to negative 6x squared over negative 6y, which is just x squared over y. Okay. Okay, so to find the second derivative, we're going to take the derivative of what we have. So we have x squared over y. So if we look at this, this is going to need quotient rule. So dx of x squared over y is going to need some quotient rule. So this will be my u, this will be my v. So u equals x squared, u prime would equal 2x, v equals y, v prime would equal dy dx. And quotient rule is v u prime minus u v prime over v squared. So if we write this out, we get y times 2x minus x squared dy dx all over y squared. Which is equal to 2xy minus x squared dy dx all over y squared. So that is our second derivative. And we know dy dx from our first derivative, so we can substitute that into this, and we'll get 2xy minus x squared over y all over y squared. So since we want to know the second derivative at the point 1, 2, we are going to substitute in for x and y. So second derivative at the point 1, 2 should look like 2 times x, which is 1, times y, which is 2, minus 1 squared times 1 squared over 2 all over 2 squared. And when we do that out, we get 4 minus a half all over 4, which is equal to, okay, so that equals 7 over 8. Okay, so down at the bottom, we're going to use power rule to find the derivative of radicals. So this is a little bit of review, but needed, because I've noticed that some people are not able to find the derivative of radical functions. So first thing we want to do is rewrite this function so that it's in an exponent form so that we can use our power rule. So we know that cubed root of x squared can be rewritten as x to the 2/3. And we know that to write a fraction in exponents, we just make the exponent negative. So we have 6 times x to the negative 2/3. So that is our function in exponent terms. So we want the derivative of 6x to the negative 2/3. So using power rule, we'll bring down the negative 2/3 and multiply it by 6, which will give us negative 4. And then we'll subtract 1 from our exponent, which will bring us to negative 5/3. Okay, and to go backwards and rewrite it as a radical, the negative exponent means that we have a fraction. So we have negative 4 over x to the 5/3. And then the fractional exponent means we have a radical. So we have negative 4 over cubed root of x to the 5th. Alright, and for the last problem, we can rewrite this as tangent 5x to the 1/2, take the derivative of that. This becomes a multiple baby mama rule. So this is the mama, and here's the baby. So we have 1/2, and then keep everything. Tan 5x to the negative 1/2. And then the derivative of tangent 5x. So that would be the mama. And then we would need the derivative of the baby, which is 5x. So derivative of 5x. So we have 1/2 tangent 5x to the negative 1/2. Derivative of tangent is secant squared 5x, and the derivative of 5x is 5. So we can rewrite this using simplification. 5 times 1/2 is 5/1/2. Tangent 5x to the negative 1/2, right? The negative means it'll be a fraction. The 1/2 means it'll be a square root. So we have 1/square root of tangent 5x. And then we have the secant squared 5x. And we can multiply all of that together, and we'll get 5 secant squared 5x all over 2 square root tangent 5x. Okay, so the main thing about the chain rule, which we also call the baby mama rule, is that you want to make sure that you get the derivative of every piece of that function, right? We want the derivative of the exponent, we want the derivative of the trig function, and we want the derivative of the x term, right? So the derivative of the exponent would have been 1/2 and the negative 1/2. The derivative of the trig function is secant squared, and the derivative of the x term is 5. So for each separate piece in our chain rule, in our function, we want to find the derivative of each piece of that function. Okay, so tomorrow you will receive the problem set for this week, and the quiz reminder is on Thursday this week, not Friday, due to Veterans Day.